Can you see the screen?
Yes, sir.
Okay, good. So today we will be mostly talking about some of the fundamental principles of learning that sometimes we forget to follow and then end up in fitting our hypothesis in a bad manner. Or sometimes these are some of the essential ingredients we need to keep in our mind to design the learning algorithms when we proceed to solve any problem, machine learning problem. So we call this as core learning principles. So one of them in this core learning principle is you need to find simple hypothesis first of all. So one of the one of the thing that we already studied, that whatever we are developing in terms of hypothesis, that hypothesis need to be simple. Simple has many ramifications. For example, why we need simple? Because we have seen that a lower order polynomial rather than a higher order polynomial, if they can fit the data well, they will also do well out of sample performance, and it will be easy for generalization aspect as well. So we also look for the simple hypothesis in the generalization aspect of it. But here the notion of simple comes from a very popular regime which is called the Occam razor. So this Occam razor is a term coined by the William of Occam in 14th century, which means that from a data you try to find out your machine learning hypothesis in such a way that as razor trims, then you go on trimming it to make it simple, and you stop at a point where that hypothesis is simplest but not simpler enough so that it do not fit the data well. So you just put a raise, you just trim it to that much extent so that it becomes a well representative of the data. That's the whole the name convention comes from this fact. So according to that quote of Einstein, that the data should not be made, I mean, the explanation of the data should not be made as simple as possible. It should be made as simple as possible, but not simpler. So here we need to understand two things in particular, that what does it mean to be something to be simple? So what is simple? And the second thing, we are always arguing that simple is better. So simple is better, but why? So these two questions we need to understand. So let us try to ask the first question, that what do we mean when we call that a hypothesis is simple? So you can see that there are two things we argue for in case of simple. One is the complexity of hypothesis that we derive, and the second is the complexity of the hypothesis space that we have in our hand, right? So when we say the complexity of the hypothesis, we usually talk it as order of polynomial if we are trying to fit the hypothesis in terms of a polynomial function. So if our hypothesis x is a polynomial function, we want to know what is the order of polynomial. Rather than this, it is this one we prefer to be simpler than this. Also, we sometimes use a minimum description length, MDL. So minimum description length says that suppose I want to fit a billion uh, a data containing 1 billion entries. Suppose I want to fit 2 to the power 1 billion minus 1, this number. So as you can see, if we try to represent this, this requires how many number of bits to represent this? this 2 to the power 1 billion minus 1. If we represent it binary, I will require around 1 billion number of bits to represent this, right? However, if you see the description of this number, it is 2 to the power 1 billion minus 1. This is small. So if you look at the description, it is 2 to the power 1 billion minus 1. This is what do we mean by the description. So sometimes it is not that how you represent the number computationally gives rise to the complexity of the hypothesis that has been thought of, but it also matters if we look for the minimum description length, it also matters that how you express it in terms of description. If that is less, sometimes we call it at this is very less to express. However, we shall restrict ourselves in this particular notion order of polynomial that we have seen to be one of our guidance when we seek for a hypothesis H. In contrary, any mathematical proof when we give, we do not bother what we acquire. Rather, we bother for the full set from where we acquired this, right? So therefore, we try to derive mathematical notion of complexity of a particular model by finding it from VC dimension, right? So VC dimension is applied directly over the hypothesis space, not for a single hypothesis. And we say that something can be generalizable or something is complicated in terms of learning if the VC dimension is higher. We cannot scatter in less number of points. Or sometimes we also use some measures called entropy based measures, that if the entropy is in between, so that is you do not know 1 bit is required for the entropy to be half. I mean, you need to represent that. If the entropy is towards 0 and towards 1, therefore it contains less information and therefore multiple number of bits could represent that same thing. So this also is a measure about what you are trying to represent. However, you see the measure from what you gathered, right? Is this notion clear? I mean, what is according to a machine learning expert simple is, that is the small h. What is according to mathematics, the simpler is, that is the complexity of capital H.
Yes, sir.
Okay, so in pictorial form, if we try to look that suppose this is our hypothesis space. Now there are many hypotheses within this. So now when you try to solve a problem mathematically to know the complexity, you need to figure out this space to know the complexity. However, when I pick up something as my H, I only see this fits my data perfectly or very well, all my data points. So I see that what is this, how much complex is this? Oh, it's a 10th order polynomial. Then this is not so simple. It's a second order polynomial, it's simpler. But however, from proving it from a mathematical point of view, we need to see what is the hypothesis space contain. It's only 10th order or it's a mixture of till 100th order. So then mathematics try to find out their VC dimension and the complexity of the learning and all that we have studied in the course. Now, since there are two notions to relate now, so immediate question comes that what is the obvious link between them, that I try to see how good I learn from the complexity of this. Mathematically, we prove it by this. So the notion of how simple it is also depends on how you get to this one, because let's say I got after learning a hypothesis H and it takes L bits to represent. It takes L bits to represent, right? So therefore I can say that this could be, I can easily infer that this could be potentially one among 2 to the power L elements of H, right? Because I represented it in terms of L bits, definitely it should belong to at least 2 to the power L elements of H. Maybe H belongs to more, but it should be H must contain 2 to the power L elements because I have chosen an L bit representation on 0110 from this. Agreed?
Yes, sir, agreed.
Therefore, the complex, so now see, now we are trying to induce what? We are trying to induce a counting mechanism to link it, which means that simpler is the representation power of your chosen hypothesis, lesser is the amount of search space in the hypothesis set, right? So there is a relation between them. So obviously, in terms of real valued parameters, what we see that 17th order polynomial, suppose my H is a 17th order polynomial. What can I infer from this about the capital H? That if you have to fit 17th order polynomial, if you try to look at the 17th order polynomial equation, it basically has some term a0 plus a1x up to a16 x to the power 16, a17 x to the power 17. That is my 17th order polynomial. Now, the parameters are also many. Therefore, if it is real valued, so each of them can take real value. Therefore, you can see the space that it belongs in the capital H is also higher if we express it in 17th order. So what we try to make sure here is that the simple, in terms of us, though we look at simple from the hypothesis that we finally found, it has a relation in terms of the number of hypotheses set we have. Second order polynomial must be one among a few members in the hypothesis set. 17th order polynomial is one among many. So we say that the more complex our H is, it is one among many of the hypothesis elements from which I can find it, right? So that is the notion of simple according to our end. But there are exceptions. Can anyone predict where is the exceptions we get it? Though it sometimes looks complex, but it's actually we get a simple hypothesis from it. Though H is complex, but we get a simple hypothesis. Can you tell me an exception?
Using regularization.
Just
So
little loud.
regularization.
Support vector machine. See what do you do in support vector machine? In support vector machines, we have some of like this, and maybe we have some like this, and then we transform into higher dimension space and do all this. Then finally found out that these are my support vectors. One is this, one is this, one is this, one is this, and maybe this one. So you see that though it looks complicated polynomial, that means H that I gathered from is one of the many things. But how do I define that? I define that in terms of support vectors, which is one among few. So it's an exception. But however, I mean, we got an essence about what does the simple, by a simple hypothesis, what do we mean? That what we get is something that relates to the hypothesis space. And if we can get it from one among many, by looking at what we get, we found that it has came from a many set, then obviously it's a complicated one. It's not a simple one. Now the second point, why simple is better. For that, as I promised yesterday, I will go on giving you little small puzzle to think about. So here goes the first puzzle. Suppose a very naive way I'm trying to tell it. Suppose some astrologer knocks your door every morning and predicts how your day is going to be, how your today is going to be. Will it be good? Will it be bad? Let's keep it just in binary. So he comes in the first day, he knocks your door, he tells that today will be good. He comes in the next day, and you found that your day was good. He comes in the next day, he again just told you free of cost that today you will be bad. And you open, and the whole day gone, and the night you ponder, you see that yes, it is a bad. He comes again in the third day, tell to you, today will be bad. And somehow you found out that it goes bad. This happens consecutively for the 5 days. Now you are wondering what is happening. How do they know? How do they learn my day beforehand? Now suddenly what happens in the sixth day morning, you are very eager that when he will come, just to verify that, I mean, how he is doing it. So in the sixth day morning, he comes and he asks you, did my all other days went as I predicted? You said yes. He asked then, did you want to know more? You are obviously curious. You say yes. He asks that, give me 100 rupees. What will you do? Is the context understood where we are in?
Yes, sir.
Consecutive 5 days, one so-called astrologer you do not know matched your verdict beforehand. Sixth day, he was asking me, he's asking you, give me 100 rupees to know how today will go. What will you do? Should you pay or not pay?
Pay, sir, because his prediction was right, so probably it is.
You haven't get many
Sir,
scams.
can we apply? Sir, can we
Can
apply
we?
any machine learning approach, prediction approach here? Then calculate
Okay, let me see other
ourselves.
suggestions. Okay, I got your suggestion. Are there any other suggestions from anyone?
So expectation of probability that he will predict correct.
Okay. Actually, let me give you a hint. He is not doing any prediction, any learning. He is doing a deterministic approach. Let me tell you why. And you'll be laughing at me after I tell it why. He came to you 5 days, right? At the first day, among the 5 days, at the first day, he goes to 32 neighbors in that locality. He predicts 16 neighbors that your day will be bad. 4, 8, 12, 16. And he predicts 16 neighbors that your day will be good. Right?
Yes.
Somebody will match, somebody will not match. Suppose you have a 0, you have a bad day. Next time, he goes to only those who has been matched. Half of them he predicts. Half of them he predicts the next day would be good. Suppose you are in this half. Next day again, he went to those people whose both days matched. He does this. Suppose the next day was this much. He goes to this people and do this. Suppose the next day was this. He goes to these two people and do this. Suppose the next day was, let's say 1. This is you now. This is you on 6th day. Right? Because your first day matched, second day matched, third day matched, fourth day matched, fifth day. Fifth day also matched. So now you here. Here he doesn't have any sample left more. So there he asks you, pay me 100 rupees. Get it? He is not doing any prediction, isn't it?
Yes.
But why I bring this puzzle to you, because of the fact everybody is with me, right? I mean, it's not a prediction. It's just he's just sampling everyone.
Yes, sir.
Yes, sir.
Yes, sir.
So why I brought up this puzzle is that, see, it is one among 2 to the power n, right? There are members here also at each iterations. He can narrow it down. It is 1 among 2 to the power n. Now, why you are so much greedy to give him 100 rupees? Because you are the lucky one, which means even if your sample space or the hypothesis space is huge, if very simple hypothesis fits all the data points, you are tempted to go by that without looking the full hypothesis space, right? For example, I give an analogy. Suppose you have a set of points, n points, and it looks like this. You said, wow, it is this much. So you do not see the constellation of all these points may form like this. However, you picked up something which is of 2 because you need to pick ax plus b, these 2 parameters. So better or simpler doesn't mean elegant unless you see what is the cost is being paid. And the cost is being paid that comes from the hypothesis space that you search on. Right? But eventually, if you can fit something with the simplest one, you are tempted to go there. That is trap number 1. So always try to think under which hypothesis scenario I am doing this note. I am just refining it to my one hypothesis as a solution. If that hypothesis space is too large, then you have to accordingly pay to it. Okay, it doesn't mean that I got a simple hypothesis that is a eureka moment, but you need to see from where you are converging. It's the same question of bias and variance, right? So you converge into very good, but your convergence criteria through search is very, very huge. So mathematically, fewer simple hypotheses than complex one. In mathematical notion, we can write it that you have fewer simple hypotheses than complex ones. So how do we know that? Remember this was our growth function. So under this growth function, among all, so this is the probability that you will fit data with any one of these growth function. Now in the postal scam, it apparently turns out to be 1 out of 2 to the power n for you, the hypothesis that you got finally. Consecutive 5 days matched. But this does not account to be simple, because simple is better when, so I can say simple is better when it performs well also in out of sample. Now to know the out of sample, you need to know the full hypothesis space, because this is the representation of out of sample fitting as well. Right? So therefore,
Yes,
when
sir.
we say simple is better, it not necessarily means what you converged into, as opposed to where in the first place we saw that if it is a less order polynomial, that simple would be better. But depending on the constellation of the data here, in terms of constellation of the points, what is the space you need to traverse to get into that also accounts to your complexity. Don't forget that. Right? As the astrologer case, as the astrologer scam. So see, the question is that this is nothing by 5 days coming to your home. He might be spending 10 bucks to the rickshaw or something. So 50 bucks he spent, he is now charging you 100 bucks in the 10th day, in the 6th day. So it's a very it's illegal, but it's a business. Now, the second thing that I would say in this line is that you also need to think, when you fit with the simple data, how much evidence do you have to satisfy and falsify the data? Let me give you an example. Suppose I have 2 data points, right? I got only 2 training examples and I need to fit it. And you say, well, I got 2 examples, so what at most can we do? I just can fit it with a line. Okay, so to be more clear, just let us make it over the line. But see, and somebody else, somebody else has experimented with 3 points. And let's say he or she has got the 3 points in this line only. So he or she has got this 3 point in this line. Okay. So now my question is that who is the better? Who is in better position to say my hypothesis will be more predictive according to you? Is it person A or is it person B?
B,
Why do you think so?
because its hypothesis justifies in more points than the hypothesis A.
Sir,
Yes.
sir, 3 is still less number of training data set, na? Then how we can define it 3 is better than 2?
But suppose you did not get more, then which one is better?
Comparatively, B, no, second one.
Yeah, you are right in guessing it, but here is a notion which is called falsifiability. The notion of falsifiability says, see, 2 points, there is no other way than there is no other way than putting a line to connect it. So 2 points can always be connected with a line. But this guy has provided one more point as an evidence. Because you see, 2 points can be fit in a line, but his evidence could have been here, could have been here, could have been here. Now, due to this third point he or she has experimented with, he has better chance in making the claim in terms of one evidence. So he has made one evidence. This person has made 0 evidence proving his H1 claim. This person has made 1 evidence proving his H2 claim. So the rule of the thumb is that if you cannot falsify your given claim by the data set you have, then you are not making a justice in your learning. Right? I think agreed philosophically also it is.
Yes, sir.
Right? So this is one of the notions that sometimes people forget, that providing evidence to falsify the data. So that's why when we say, so why I bring all these notions into simplicity? Because when I say that I will fit something perfectly with a higher order polynomial, now you see the point that this polynomial definitely will fit these many number of data perfectly. But do you provide any additional evidence? As in this case, see, 2 points will definitely fit perfectly in a line, but there are no evidence to falsify your data. So that means that you are losing the simplicity barrier and coming out. You need to be much simpler than this. Rather, in the first case, the first guy, if he would have chosen a line which is axis parallel, then he would have proven it, because axis parallel line can be fit by only 1 point, then 1 is an evidence. Right? So this is what we want to mean as the simplicity of a hypothesis, the notion of simplicity and Occam razor, to be more formally stated. Any questions up to this point? Okay, let us proceed. The second thing is called sampling bias, which is very dangerous. Here comes the puzzle too, which is a historical true fact, but the puzzle goes this way. In 1948, there was a presidential election in USA, and the two candidate was, one is Truman, and versus he stands with Dewey in the CCE. Now, the poll happened, and at the night, the result will come out the next day. So that day in 1948, it was a postal balloted poll. So the counting and the result will come 1-2 days afterwards. Then at the night after the poll ran, a newspaper agency called a section of the people in the all over the US. I mean, I'm not saying it is biased towards the Texas or something. They called many people all over the US, and from this sample, they tried to predict who is the winner is. And what they did was that they predict this person wins as per the prediction of the newspaper. And what they did, they already published the newspapers at overnight that Dewey wins over Truman. And guess what? After one day, when actual result happens, the winner is this person. So now you have to tell it that what went wrong.
What now?
You have to tell me that what went wrong in the prediction.
Data set.
The previously training dataset was wrong with respect to the next phase of dataset.
The next phase is actual result. I mean, it's not a data set, it's the actual result of everybody.
No, before the night, whatever the dataset should become is just false
Okay.
with respect to the
Okay,
next.
since you are thinking on the data set line, let me also give you one more query on that. Do you believe that if that day night the newspaper agency does this polling, let's say 100 number of times and takes the average winner, then that newspaper agency would have been doing better? Instead of let us take this problem very simple. Suppose the newspaper agency has polled 100 people. I mean, to do a rough estimate. Suppose there are 1,000 people in US, the newspaper agency polled 100 people, and then they predict a winner. I am saying that if they repeat it multiple times by doing the same thing again and again, and then finally come up with the prediction, does their prediction will do better? Randomly picking 100 people and call them. Why I push this one? Because I will relate everything, common sense with mathematics, as I every time told. Why I told this? Mathematically, the in-sample error should track the out-of-sample error within a confidence bound. You may be tempted to think this is the problem, right? Because I say it's not perfectly, I mean, some tolerance is not perfectly, we are not allowing it. We are allowing it with a tolerance, right? With a confidence. So maybe the prediction went wrong because due to this fact, it's a question of possibility versus probability. You are saying probably Truman would have won, but there is a possibility that this sample has done that. But you know, where is the bias here? I mean, he will laugh at me by seeing it. I told that it was done over a phone call polling of 100 people they called. At 1948, phones were only accessible to richer people. And guess what? Richer people preferred Dewey over Truman. That's why I told if they have repeated this set over 100 other random people as well, the verdict of them, predicting verdict of them wouldn't change because of this small sample bias, which prefers higher or aristocrat people only in the sample, not the overall population, which is mostly favoring Truman. Right? So here comes the second confession, that if the data is sampled in a biased way, learning will provide biased outcome. So if data is sampled biasedly, learning will output biased hypothesis. So another example, which I mean, so how to get rid of this? First of all, so what happens is that suppose this is the distribution of the people when you try to train, and this is the distribution of the people, a slightly shifted like this when you try to test. What people do sometimes, they put a weighted average while training, that not all the data will carry equal weight in training. Suppose my data 1 point will carry weight 1, when I do it the data 2 point will carry weight 2, and they try to see from the domain knowledge, they try to see that which of the cluster of the data I will try to put different weight. In this way they nullify the bias. And it also happens in credit approval many times in the bank applications nowadays, because remember the credit approval problem where you have to have age, salary, years of
Yes, sir.
residence, and all this contributes to that your credit is being approved or denied. Now from the bank data, suppose somebody wants to build a machine learning software to do this. So I want to build a machine learning software. So what the bank data only contains is the members whose credit has been accepted, right? The bank data will not contain somebody has denied, because he came, he denied, he has no record in the bank. Now see the bias here. If only the accepted persons are in your data set, then suppose in the bigger picture you are trying to do something, finding out who is the acceptance set. Suppose these are my acceptance set. Now when you classify, your classification boundary is obviously going to be shifted more towards the acceptance region, right? Suppose these are my rejected sets, and here there are some people who are little bit volatile, but they are mostly very much profit worthy, because if you give them, they may pay in time and all that. Rather than your boundary is somewhere here, due to this sample bias, you miss out this space. Agreed, because you have only accepted data. And I said that if your data is sampled in a biased way, your learning is with respect to data. So your data is best fit in this region. So you are saying only this region to be positive. So that means you miss out this point to generalize. Agreed, this is what we mean by sampling bias. Questions? The third one is the most dangerous, and people knowingly, unknowingly step upon it, which is called data snooping. I already mentioned it when I do a transformation and all. This is very dangerous, and this is the most worrying thing on machine learning. So so that's why in your project 1 and 2, our TAs and we are constantly telling you that do not look at the data. Just try to give your machine learning algorithm in a generic way, then try to see how it performs. That's the warning is because of data snooping aspect. What is data snooping? See, if your data is being compromised while you are doing the learning, then your outcome will also be compromised. It's a different kind of bias you will get in the outcome. And that bias is due to the fact that you looked into the data and you yourself played as a machine learning expert. Your brain also is there in the hypothesis space. And therefore, you found out a data which perfectly fits, but you yourself learned for it. Your machine learning program is not that much equipped. Do you get it? I mean, let me give the same example which I gave it in the last time. Remember, we have a distribution like
Yes,
this,
sir.
and we have a negative points like this. Now, obviously, you can understand here the classification boundary will look like this. Now, what I have to do in terms of to do it in linear separator, I have to transform it into Z space. This side is x1 and this side is x2. To have a linear separator, I have to transform into Z space. And Z space by kernel, you know now the kernels. So Z space is effectively all the combinations that I can get of all my x1 and x2. This is the full Z space representation in terms of the kernel. Now what we did, well, it looks like these points, if we could make the center here, it will look like a circle and all, then you can reduce the Z space. Why these terms are required, I do not understand. I just need these three terms to perfectly characterize it. Now again, upon looking up, you see the data, well, why these three attributes? See, the number of attributes increases the number of dimensions, which increases indeed the learning complexity and everything. And also the generalization boundary, it creates a problem. So, well, it's a distance from the center and all of the nearer ones I want to classify. So then I would reduce the attribute more. And if you look further, well, why two attributes are needed? I can do it in just one by having this. If it is more than that, it's outside, it's less than that. Now see what happens. From here to here, you learned. Your algorithm doesn't learn anything. From here to here, you again learn. From here to here, you again learn. Which means your algorithm stays as it is when it was doing this, this, or this. But if you thought your data distribution is like this and your algorithm has captured it, you are wrong, because you yourself is a part of the algorithm that you have not charged for. Which means that you thought if the hypothesis space is only of one parameter, actually it is not. Actually, it is of multiple parameter hypothesis space. You navigated the data and reduce it down, so you are not charging your brain. So that's why the outcome what it may arise to will not generalize well beyond the data set that is given to you. A very practical example, which is our next puzzle. A very practical example is to predict the rate of dollar versus rupees. So what happens is that what we did is that we have a set of previous years data, and we will try to predict over 20 months, looking at 20 months from delta. So delta minus 20, rupee value delta minus 19, rupee value delta minus 18. All of this we will see delta minus 1 rupee value, and then we try to predict what is the dollar value at delta. That's the game. Now we are given with a set of data, then we are traditional method, all the set of data, we just do it as a data train union data test. First of all, we have this data over the years, so we need to normalize it. So we normalized, and then the normalized data, we just put it into test and train bucket. We normalize in terms of the mean, because as you can see that these data, if you look into, it's a fluctuating market space over the number of days. So if I put it here, the number of days, and here the rate, it's actually will look like very fluctuating kind of a thing. And since therefore I need to do a normalizations and all. Then you have an experiment over this, and finally you found out your prediction is absolutely, let's say your prediction is just like almost matching very well. You fit it, minimize the errors, stochastic gradients and all linear regression thing, and you do this. And you say you are doing absolutely perfect because your error rate is gone. But actually, when we go with the real data and go with the actual experiment, what is happening is that it just performs like this. So the reason being, I am telling the answer. Now you have to justify where it happened. The reason is data snooping, but where it happened. Did you get the problem, the puzzle, what I have asked?
Sir, can you repeat it once?
What I'm saying is that I want to predict the forex values of rupees and dollars. From the rupees, I want to predict the next forex value exchange rates, right? So what I look
Yes.
upon is the past 20 days record and try to predict it. And in this way, I will just keep on doing a linear regression to predict it. So to validate, I just normalize my data and put it into a training set and a test set, and then train my machine learning algorithm, and absolutely found very good thing. In the test set, it performs brilliant. And this is the red curve is the test set, which is performing brilliant and is going with the test set according to the test curve. But in reality, when I deploy my model, then I found this blue curve. So what went wrong? Well, the answer is data snooping, but you have to tell me where the data snooping happened.
Data
Obviously,
normalization.
with respect.
Yeah, one by one. Someone is saying data normalization. Where in normalization it happened?
Sir, we reduce our original data by mean, so we change like first it was in range like 1 to 100. Now we are after reducing, we are after normalizing, we reduce it between specific range -1 to 1. Then learn model has learned to predict between this range -1 to 1.
-1 to -20, 20 days.
Uh, um, I'm telling that so after normalizing the data, the range has become from -1 to 1. Initially, it was 1 to 100. So our model
Yeah.
learned to predict between -1 to 1.
No, that's okay. But then you are again going with the reverse normalization to plot the data. That's how we do. I mean, otherwise, why do we normalize? There is a role of normalization, right?
Yes.
You are
But
right
it
in
will.
guessing that there is a problem here, but not the point that you are mentioning is here applicable. Just let me give you. It's a very fine, very thin amount of data snooping happening. You normalized over whole data. How do you normalize? You normalized over a mean, right? Over the whole data. Now, when you divide it into training and test, with respect to mean, these two, you should have been normalized the data with the training set and the test set separately. Did you get it? Because see, the training set could have been a different zone than in the test set. So normalizing with the same mean make these two things not at par. When I say I will normalize, what does normalization mean? Normalization means over the data set that is given to you for training, you have to normalize, and also for the test. So for the test, the set of data that you get, you take a mean of the test to normalize. For the training, the set of data that is to be given, you take a mean of the training to normalize. Then you apply this, and then it will obviously follow that whatever is the actual trend. So the whole point is that this may be a pathological example. The whole point is that it's very thin amount of data snooping is happening, which has a disaster in the performance. And it's unknowingly it happens, see some slip. It's a very low slip. And you are seeing that I fit the data perfectly. You are not even bothered to think about data snooping has happened or not, because you are seeing I have fit the data perfectly. What else I want? I will report this hypothesis and get money for the company. But you have to just cross check once that how compromised your data is in every step of the operation. The second thing that we always forget and try to do is trying different model. It is absolutely perfect to try different model to find out which is better. I try SVM, I try decision tree, I try neural network, I try any other, let's say, Bayesian classifier. But finally, where we fall short in this fact is that you try and found out, well, SVM is the best. So, okay, I give the support vectors and I charge accordingly. This is the VC dimension, complexity, etc., etc. But what you forgot in this process, see, your data set is fixed. You first go with SVA, you first go with, let's say, Bayesian classifier. Well, my data set is not getting that well, I'm not getting performance. Then you go with neural networks, no, that is not. Then you go with decision tree, no, that is not. But what you forget here is the fact that your hypothesis space now is not only SVM, but also the decision trees, the neural networks, the Bayesian classifiers, right? So accordingly, you charge the VC dimension for that. Not only with the support vectors, you go for it. So you will say that once you figure out this one, you will say, well, it's a best generalization. I am getting it because it's absolutely doing good over it. But wait a minute, this generalization is not over only the support vector. This generalization has a role to play in the whole VC dimension of the hypothesis space that you have started off with, not you have finalized with. This is one of the major mistakes we sometimes make to match the particular data. So there is a very, very popular quote on this. The quote goes like this, I think by Hinton or something, that if you torture the data long enough, it will confess. So we are torturing the data so long that Bayesian classifier is not confessing, neural network it is not confessing, the decision tree is not confessing, finally support vector confess. So the bottom rule of the thumb is that when you also reuse a data set one after another, charge accordingly the penalty of the complexity of the data space in generalization as well. So obviously two remedies we found out for this data snooping. One is discipline, which means that you should not look into the data, and cross-checking. The second one that we already see, that you need to keep an account for how much you penalize for it, like this here. It's not that you got a best result after trying out 100 different models, but you are saying you are only mathematically trying to establish the generalization bound with respect to only one model that you converged into is not the fact. Similar the case when we transform it to a different domain, you are using your brain for that. So obviously you need to charge for every particular attribute in that transform domain, not only what your brain converges and give you it as single attributed model, right? So here comes the last question. I will end with this because all these concepts falls here too. That suppose there is a stock market broking company which has 50 years worth of data. It's a simple question. Now you can easily answer. So it has a 50 years worth of data. Now it's a buy and hold share. It holds for something a share and then sold it. Now it need to predict that which of the company's share will be more profitable if we keep it for, let's say, 20 years or so. So what they did, they traded for, they collected data for all top 500 such companies over the past 20-30 years, and they strictly followed buy and hold policy and would make up profit, but they didn't. Can you say me why it happened?
So they can able to predict correctly.
No, they couldn't predict correctly because that's what the problem lies. See, they took 50 years
Sir,
of data.
then-
They took top
Oh.
500 companies, currently traded 500 top companies. They followed strictly the regime. They do not normalize like that as we have seen there and all that. But still, they do not get a profit. Where is the bias and
Sir,
snooping both happened here?
Sir, bias is mainly they have collected the data from the top 500 companies, but
Perfect.
all
Perfect.
the companies are not top.
Perfect.
First,
Yeah,
and
and
then
snooping?
snooping is obviously as per they are taking the top company set. That's why the
No. That is
data
bias.
set
That is
should be.
bias. That is bias.
No, I am telling about the data from that company will be just moving on some similar surroundings, not to
No,
cover
see,
the total.
no. See, that is not snooping. You are just getting the data from them. I mean, you are not looking into the data.
Oh, I cannot look into that data. Okay.
Anybody? See, it's a buy and hold share, right? So effectively, you just took 50 years of data and you are trying to predict it. So if it's a buy and hold share, so you are only doing this over the last 50 years of things, right? Recently traded company is a sampling bias, but you are doing this over your data, your data snooping because you are looking at the last 50 years only. Okay, not the generic, the full setup.
Yes, sir. Yes, sir. I got it. Huh?
Yeah, that's it. I mean, I will not tell you the clue. I mean, you think it. I mean, it's not such. I mean, it's something that you need to understand what is happening. But to summarize, I mean, we are ending time. So to summarize, we have three things in our consideration now. Apart from whatever we have learned, very good mathematics, very good algorithm, we can write it, wrote the project, everything. But three principles you need to make sure when you do somewhere and in practice. One, simplest is the best, but not simple. It should not be as simple that it cannot fit the data. I mean, then you compromise. But more complex means you are also fitting the noise along with the data. That should be prohibited. The second is that avoid sampling bias. So when you get the data, you ask that from where you have gathered it, what is the variance and all that. Absolutely, that is not data snooping at all. You are free to ask that, is it a monsoon weather data or what kind of data it is. Attributes of the data to ask is not data snooping. But to get more, know that the sample is being distributed enough, otherwise you need to make a weighted assumption on that during training. The third thing that we've seen is the data snooping aspect, that either you need to follow strict discipline that you need not have to see. So whenever you do practical problems in machine learning, do not see the data. First freeze your algorithm, then go by data. And if you need to try for different model, suitably account or charge for them. That's the three principles that you need to know. So this is, till this, after computational learning will be our syllabus for the last test. Okay. So as per the syllabus of machine learning, only one thing remains, that is reinforcement learning. We will cover it in the next week. And then the next 3-4 classes will be on the advancement where we can reach and the open research questions. So that's all from today. Thank you. Any questions? Okay, Dipankshi and Ashish, you will be taking the scribes for today. I am stopping
Yes,
the
sir.
recording.